SOPHIA process was developed at the end of the 80s. The goal was to achieve a controlled and faster solidification. The aim was also to minimize the dependence of the strength values on the wall thickness. As can be seen in the diagram on the right, the aluminum is poured into the hot ceramic mold around 750 degrees for the mold and for the metal. Then the mold is then transferred into the SOPHIA chamber. Lowering into a cooling medium of about 40 to 60 degrees is now computer controlled. The lowering speeds depends on the geometry and wall thickness. By using the SOPHIA process, a finer and denser microstructure is achieved in combination with higher strength compared to castings from conventional investment casting. The plant in Soest is one of 4 plants worldwide where the SOPHIA process is used. The sketch on the right, you can clearly see the principle of the process. When lowered into the cooling medium, the hot ceramic mold is cooled down very fast at the contact point and the melt solidifies in this area. The cooling medium slowly penetrates into the porous ceramic shell and cools the aluminum further in this area. By lowering the mold further, the solidification front is now directed from the frame, that's the lower point of the cluster, to the top feeder. The left-hand image shows the temperature gradient during the SOPHIA process. While the lower part of the ceramic mold already has a temperature of around 200 to 250 degrees Celsius, the temperature above the cooling media is significantly higher. It's above solidus temperature. And this allows to feed all sections in the proper way. Here you can see a more detailed description of the SOPHIA process. After casting, the hot mold is transferred into the SOPHIA chamber. Depending on the volume and the wall thickness of the part, a part-specific program is developed and stored into the SOPHIA system. In this example, the SOPHIA program consists of a total 4 steps. In the first step, the mold is moved into the cooling medium up to the lowest edge of the component. Solidification is initiated at the stopping point. After a certain time, the lowering device continues at a defined speed and then just stops below the upper edge of the component. The holding times and lowering speeds must be selected so that the solidification front is not overtaken. Additional steps can be installed for more complex parts. After the component has solidified, another holding step is inserted above the component. Finally, the cluster is lowered completely into the cooling medium so that the feeder level solidifies. After the complete cluster has solidified, the cluster comes out and then you can work on it later to remove the ceramics and go on in the process. Here we prepare 4 micrographs with different magnifications from SOPHIA parts and from conventional investment casting. The comparison of the 2 micrographs shows the clear difference in the microstructure. The silicon or eutectic is much finer and more rounded in the SOPHIA process. In addition, the distance between the dendrites and the dendrite arms is smaller. This is due to the high local solidification speed at the contact surface of the cooled ceramic mold and the liquid metal. The use of a modifying agent such as sodium is not necessary. On this slide, we want to show why we use SOPHIA. The following options are available to increase the strength. Selection of a different alloy, melting treatment, increasing the solidification rate, thermal mechanical treatment, and heat treatment. The alloys used offer the optimum solution in terms of castability, strength, corrosion resistance for many applications. Melt treatment like grain refinement and degassing and heat treatment are carried out as standard in our operation. Thermomechanical treatment is not used for cast part except for the hipping process in some limited cases. Since the other options are ruled out, the solidification speed must be increased to reduce the dendrite arm spacing in order to obtain a finer structure. The relationship between the dendrite arm spacing and mechanical properties is shown in the diagram on the left. In the conventional investment casting, values between 60 and 150 microns are achieved due to the lower and slower solidification. In order to achieve smaller dendrite arm spacing, the melt had to be cooled in a targeted and directed manner. Parts cast using the SOPHIA process typically have a dendrite arm spacing of between 30 and 60 microns.